Now I've saved the best for last. By best, I mean the most difficult, algebraically speaking, techniques. So we have polynomial division. If you remember polynomial long division from pre-calc, you can only use if the degree of your numerator is greater. Oh, yeah. Well, greater than or equal to, I should say. Greater than or equal to the degree of the denominator. In other words, if they are polynomials, you cannot use it if the degree of your numerator is less than the degree of your denominator. It would be impossible. Now this one, you can see the degree of the numerator is 3, the degree of the denominator is 2, therefore I can do this just fine. All right, so let's do some polynomial long division. All right, so it's been a while. So you make the little house, and you start off with your highest degree, and you keep working your way down, and any term you don't have a value for, you put in a 0, right? So we just don't have the constant, so I have a 0 there. Same is true for your denominator. So I have x squared. I have no x term, so I put a 0x plus 1, not plus 0. There we go. All right, x squared goes into x cubed. Well, I'd have to multiply something by x squared in order to get x cubed. It's rather obviously x, and it goes and it lines up over the linear term here. So x times 1 is x. X times 0x is 0x squared. X times x squared is x cubed. And then you subtract all of them. X cubed, take away x cubed, gone. 2x squared, take away 0x squared, brings 2x squared. 3x, take away x is 2x. And then bring the 0 down. And then you go again. So now I need to multiply x squared by something to get 2x squared. Well, that's 2. Okay, so 2 times x squared is 2x squared. 2 times 0x is 0x. 2 times 1 is 2. And then you subtract all of them. 2x squared, take away 2x squared is 0. 2x, take away 0x is 2x. 0, take away 2 is negative 2. I can get rid of that 0 in front. I don't need that. And that's the remainder right there, because I don't have any more terms to go. So the remainder is right here. Okay, now why did that, how in the world does this make things better? Well, because then, keeping this in mind, I can rewrite my integral as x plus 2 plus, and then that remainder divided by the divisor, x squared plus 1, plus 1, dx. Which you have to admit is an easier problem than what we started with, because the integral of x is easy. The integral of 2 is easy. No problems there. And then I'll just make a little note that that's the remainder that I'm using. So this remainder right here is right here. When you do this in, when you do polynomial long division in pre-calc, they often actually have you write it like that. And this is why, one of the reasons why, so you can make your integrals easier. All right, now, I still don't want to mess around with this. I mean, I could, but I'm going to make things even easier for myself by splitting up that fraction. So this was just all on the side there. It was just work we were doing to help set us up. Okay, so I'm going to rewrite it. Integral of x plus 2 plus, and now I'm going to break this up. So 2x over x squared plus 1 minus 2 over x squared plus 1. Okay, I know how to do x, the integral of x, no problem. Integral of 2, no problem. Integral of this one, you might be thinking that's a problem, but it's not, because that's a formula. It is number 19, if I'm not mistaken, on the formula sheet. It's right there. It's the arctangent one, right? So that's 19, right? So I'm going to make a little note. It's the quick integral sheet. All right, so then I'm doing great, except for this term right here. This one's going to need a u sub. I'm going to need u to be x squared plus 1. I'm going to need the du to be, oh, look at that. It's 2x dx. Well, that's convenient. All right, so let me rewrite this one more time. So it's the integral of x plus 2 minus 2 over x squared plus 1 plus the integral of, see what I did there? The 3 that I knew how to do with x's, I put them together. And then the one that I need u sub for, I'm going to rewrite it. It's 1 over u and then du. It's not even hard. It's easy also. Okay, so let's do it. So the integral of x is 1/2 x squared. The integral of 2 is 2x. This one is 2 times that arctangent formula. So it's arctangent of x, because a is 1, so it's a really easy one, plus the natural log of the absolute value of u. But the absolute value of u, I can just say what it is. It was x squared plus 1. And then I just slap a c onto the end of it from a constant of integration, and we're done. Yes, I technically skipped a step there, but we all knew that u was going to go back in, so I just thought it would be easier just to do it. All right, so that's polynomial long division. Oh, it's been a while, right? Remember that you can only use it if the degree of the numerator is greater than or equal to the degree of the denominator. But it did actually make this integral not so bad. The integral itself was quite simple. All right, it's time for your least favorite technique, completing the square. The last algebra piece. Okay, so here's the thing. When you complete the square, what does that mean? Let me write this down. Completing the square means you turn some ax squared plus bx plus c, right, into, well, actually, we generally don't do it with a, but we can. We usually don't. We usually make it like x squared. There are ways to get around the a part by basically dividing everything by a. But anyway, so x squared plus bx plus c into x plus something squared plus something, right? That's what, oh, plus or minus, I guess I should say, right? That's your goal, right? And these could be plus or could be minus. It doesn't really matter, right? But that's your goal. It's supposed to be x plus something. You're completing the perfect square. This is called a perfect square, right? When you have x plus something squared. And so when you complete the square, what you're doing is completing this square. That's the square they're talking about. Turning it into a binomial squared plus some constant. Okay, now what in the world does that mean? Well, let's look at our example. So we have negative x squared minus 8x minus 7. Sure. All right, first thing I'm going to do is take the negative out of that. All right, we generally want the x squared to be positive. So that'll turn it positive 8x plus 7. And I know what you're thinking. You're thinking, well, that factor's not relevant. That's not what I'm going for. I want to complete this square, right? Because factoring wouldn't do me any good for actually finding the integral, right? It's true, but it doesn't do me any good. I can't, find du and u and all that. Okay, so this is -1 just going to sit out in front. And now I'm going to complete the square. So I'm going to turn this into x squared plus 8x. And then here's what you do. You add something, but subtract that same thing. And then what's the thing that you add and subtract? Well, you take your middle term, if you remember this from completing the square. You take b, which is 8, you divide it by 2, and that's what you put in, and then you square it. And it goes right here. So you're going to put 4 squared in here. So you go 4 squared here, 4 squared here. You add it, and you subtract it away, because then you really haven't changed the problem. If I add 16 and I subtract 16, then I'm not changing the problem. I'm just changing what it looks like. Now, why in the world did I do that? Well, let me rewrite it. So this is x squared plus 8x plus 16 minus 16 plus 7. I'm grouping it like this on purpose because this is -1 times. And then this part right here, I'm going to turn into something squared. And then these two numbers in the back, I'm going to, here, I'm going to put these together. They make minus 9, right? It ended up being negative because 16 is negative and it's larger. So it's x plus, because everything here is positive, and it's got to be 4, right? Because 4 times 4 is 16, but 4 plus 4 is 8. I've completed the square. Sneaky, huh? And now what about the negative in front? Well, you just rewrite it. Then it's negative x plus 4 squared plus 9. Nobody in their right minds would write it like that. They would do this. That's a perfect square. All right, all of this work, all this algebra was just so I could rewrite my integral. I haven't actually done any calculus, right? But I'm rewriting by completing the square. So I took the trinomial that I had, ax squared plus bx plus c. I factored out the a because it was negative 1. And then I added b over 2 squared minus b over 2 squared. This turned into a perfect square. Notice, by the way, it's 4. Right? That's a little technique that a lot of people learn, that b over 2 is the number you end up adding. And then squared it, and then minus 9, because negative 16 plus 7 makes 9. And then I distributed my negative, rewrote it. Now, how in the world did this help me? All of this was aside, right? All of this was just kind of to help me out, because what I'm really going to do is take my integral and rewrite it as 1 over square root. And then what was there, I'm going to rewrite as 9 minus x plus 4 squared. It looks different, but if I distributed this out, FOIL it out, and distribute and combine like terms, they're the same thing. That's what we proved down here, right? By completing the square, I found a different way to write that denominator's, well, the thing under the square root, right? Called the radicand, if you want to know. Okay, so now how did this make anything any better? Well, because you have a formula for this. So if you look at your sheet right here, look at arc sine. A squared, something like 9, right? It's constant. A is a constant. Minus u, that's a function of x, squared. Yes, this is the one. So it's rule number 18 on your quick integral sheet. Okay, so if you look at rule number 18, it needs an a and it needs a u. U, this is u squared, so u is x plus 4. Du would be dx, so no problem there. And then a squared is 9, so a is equal to 3. And that's all you basically have to do, because the formula will take care of it. So by formula number 18 on your quick sheet, the integral is the arc sine of u over a, which for me was 3, plus c. And then I'll just rewrite that with what u was, and I'm done. So the actual integral was very simple because it's in that formula sheet. It was getting there, all the algebra that it takes to get there. That was where the real work was. And now you're learning, like all calculus students do, that algebra, you really need to know it very, very well to be successful, especially honestly in this chapter. Chapter 8 relies heavily on your knowledge of algebra and pre-calculus.